Ranjani Parthasarathy is a professor in Department of Computer Science and Engineering. Her area of specialization is in computer architecture and computer networking. She had guided more than 5 PhD students and currently guiding 5 PhD students. She had published paper in more than 50 national and international journals. She worked in many sponsored projects and she got IBM Faculty Award for 2008.
Welcome to the UGC lecture series in computer science. We are looking at a series of lectures on computer networks. The topic that we are looking at today would be on interconnecting LANs. So, how do I interconnect LANs or extend LANs? The devices that are used for doing this interconnection of LANs, we will be looking at devices such as repeaters, bridges, layer 2 switches and so on. So, let us start with repeaters first. So, what do I have here? I have a LAN 1 on one side and LAN 2 on the other side. So, let us say I have two stations S1, S2 on this side, S3, S4 on the other side. I have a device called a repeater which connects up these two LANs. So, what does a repeater do? A repeater is something which operates at the physical layer and forwards everything between the two LANs. So, what will happen is that LAN 1 and LAN 2 are in the same collision domain. That is, whatever is received here, the repeater will put it on this side. Similarly, whatever signal is there on LAN 2 will be put on LAN 1. So, the net result will be that all the machines which are there on both the LANs will all appear to be on the same collision domain. That is, if I have a transmission going from S1 to S2 and a transmission from S3 to S4, though they are on the two different LANs, their transmissions will collide. So, this is what we mean by saying that they are on the same collision domain. So, this is what we have with repeaters, but repeaters are simple devices which can be used for extending small LANs or extending LANs with limited number of devices. The next device that we have for extending LANs are bridges. Now, bridges again they appear something to be similar to repeaters, but they operate differently. They do not operate the physical layer, but they operate at the MAC layer. So, let us look at how that is done. So, here again we are just showing a picture with a LAN here with LAN 1 with S1, S2, S3, another LAN here with S4, S5, S6, and we have a bridge connected in between which connects up these two. So, bridges operate at the data link layer. Okay. So, unlike repeaters, bridge will not forward a frame onto another LAN segment if it knows about the location of the destination node. That is, if it knows that the destination node is not on the other side, then it will not forward that frame. Okay. And bridges use some kind of a learning technique, what is called as a backward learning, in recording the source address on transmissions. So, we will look at how this happens. Let us take, so you can see how the bridge actually would look like. So, if I have a node on one side and a node on the other side, so I have the physical MAC, LLC layer and so on here. The bridge essentially has only two layers. So, it gets something from the physical layer. At the MAC layer, it is where it transfers it from the MAC layer on one side to the MAC layer on the other side, and then through the physical layer you will have the data flow. So, you can see that bridge as such has only two layers, okay, the physical layer and the MAC layer. So, let us look at how the bridges learn this information as different transmissions take place. So, I am having a setup here which shows LAN 1 connected to LAN 2 by means of a bridge B1, LAN 2 connected to LAN 3 by means of a bridge B2. Let us assume that we have S1, S2 on LAN 1, S3 on LAN 2 and S4, S5 on LAN 3. Now, note that the bridges have two ports, port 1 and port 2 on this side, similarly port 1 here and port 2 here. So, what the bridges are basically going to learn is which addresses are on which port. So, it maintains a table of address and the corresponding port. So, let us look at the first transmission, that is, say S1 does a transmission to S5. Now, when S1 does a transmission to S5, that transmission will be available on LAN 1 and it will be received by the bridge B1. So, it receives it on port 1. So, what B1 does is, the bridge B1 does is, it says that okay, I received a frame whose source address was S1 and it came on port 1. So, it says source address S1 corresponds to port number 1. So, the address of S1 it records as coming from port 1, and since it does not have any other information in the table about the destination address, so it just forwards it on to the other port. If there are more than one port which is with, if I also had a port 3 which B1 was connected to, it would also forward it on that port as well. Okay. So, it forwards now in this case on to port 2. So, that will be transmitted on LAN 2, it will be received by B2 on port 1. So, B2 similarly makes the same judgment, that it says that okay, I have received a frame now whose source address is S1 and came to me on port 1. So, it says okay, so S1 is in the direction of port 1. So, it makes this makes this note that S1 is the address and it is on port 1, and it forwards it on to this side of the port. Now here S5 is located here, so S5 finds that there is a frame coming to it as the destination, and it will receive that frame. So this is when the first transmission takes place, this is what happens. Because if it has some information, it will use it. If there is no information, it records new information and just forwards the frame onto the other ports. So this is called as flooding the frames onto the other ports. Now let us say I have a second transmission taking place, S3 transmits to S2, right. So now S3's transmission will go on LAN 2 and it will be heard by both B1 and B2. Now look at what will happen here. B2 will hear this on port 1, whereas B1 will listen to this on port 2. So B1 makes the note that S3 address comes from port 2, whereas B2 makes note that S3 comes from port 1. So this is the second entry that we have got. So let us say now third transmission takes place, S4 transmits to S3. So when S4 transmits to S3, so now B2 will receive it on port 2, so B2 makes that entry S4 2. It also has information that S3 is on port 1, okay. So it will take it and forward it on to this side, alright. So next it takes similarly B1, if you look at what is happening here, it receives S4's transmission on port 2, right. So it makes the information that S4 is destined for port 2. So this is what it will do. Now let us say I have one more transmission now. Now this is an example of how it has learned information. Now let us say there is a transmission from S2 meant for S1. Look at what will happen here. Now S2 will be received by bridge 1 on port 1, okay. Now it already has information that S1 is located on port 1 itself, which means it is located on the same site, which means it is located on the same LAN which is connected to port 1. So what S1 now will do is, it makes note of this new information that S2 is on port 1, but it will not forward this frame on to port 2, that is over to LAN 2, because this transmission is going to happen only in this LAN. S2 is here, S1 is on the same LAN, S1 will receive this transmission. The bridge 1, since it has learned this information that S1 and S2 are on the same LAN segment, will not take this frame and forward it on to LAN 2. So this way, once enough number of transmissions take place, once all the nodes information, the address information is available at the bridges will only selectively forward frames. That is, they will not just forward all frames, but they will selectively forward frames. So this is how the learning takes place. So now bridges can also forward from different, they can connect up LANs of different protocols. That is, I could have a bridge which connects up 802.x to 802.y. So let us say I have an example here which shows the operation of a LAN bridge which goes from 802.11 to 802.3, from a wireless network to a CSMA-CD network, Ethernet network. So what would happen here? The bridge here receives a packet which is an 802.11 packet, converts that packet to an 802.3 packet and sends it on the other side. So this is also something that a bridge would do. There is two different LAN segments following two different protocols. Of course, they will have to be slightly compatible protocols. They can be connected up using a bridge. Now looking at this bridging and switching as well, let us look at what we have seen so far. So bridges basically forward traffic based on MAC level addresses, and a bridge may perform protocol conversion or may perform speed matching between different LAN types. We will look at speed matching in a short while. Bridges also provide buffering of packets. So we will also look at how that happens. And a switch is basically a fast bridge with all ports using the same frame type. It is also called as a LAN switch to basically distinguish it from an ATM switch or a telecommunication switch. So just to give you an example of what these devices look like. So a hub, if you see, is a device which will have point connections to which different nodes will be connected. But remember that a hub works like a repeater. That is, if a transmission comes in from a node A, it will be transmitted on all the other nodes as well, be on all the other links as well. B, C, D, E, F, G, H, everybody will receive that transmission. So that is how a hub works. A bridge, on the other hand, we just seen, it will learn information as to which hosts reside on which LAN and will selectively forward packets. A switch similarly will also do selective forwarding of packets, but a switch is faster than a bridge in the sense that it provides dedicated links to the different nodes. Therefore, each node can provide the full bandwidth of the LAN. Right. So that is, if I have a bridge kind of a scenario, this LAN, its bandwidth is shared between E, F, G and H. So we have a 10 megabit per second network here, the 10 megabit per second is to be shared by E, F, G and H. Whereas in a switch scenario, E, F, G and H will each get the 10 megabit per second bandwidth. So to look for appearance, it look as if the hub here and the switch are pretty much the same, right, but there is a difference. The difference is that this acts like a repeater, this does selective forwarding like a bridge. So that is what we have in terms of a switch. Okay. Now why bridging and switching? So let's understand why we need to do this bridging and switching a little bit more in detail. So one is to decrease traffic on LAN segments. Second is to extend LAN without increasing congestion. Third is to bridge different network protocols. Fourth is speed matching. Fifth is security. And sixth is reliability, basically to provide fault isolation and bandwidth balancing. Okay, let's look at each of these things in detail. So traffic and LAN size. So let's look at how we are able to handle traffic by increasing the LAN size. So let's say I have two networks A and B. Okay, this is a different LAN, this is a different LAN. I have a LAN A and a LAN B. LAN A, let's say, had a total traffic of 6 megabit per second. LAN B has a total traffic of 5 megabit per second. Now, if I join the two LAN segments with a hub or a repeater, which is possible, it just increases the traffic on both the LANs. Remember that with a hub or a repeater, both the LANs now, when they are connected up together like this, will all belong to the same collision domain. So the total traffic of 11 megabit per second, right, has to be handled by the repeater, and all of them will be competing for the same collision domain, right, for the same media basically. Since all the machines share the same media, they belong to the same collision domain. Okay, so you will find that there is more traffic which has to be handled by the two networks. Okay, this is one of the problems that we have when you are using just repeaters to connect them up. Now let us use a switched LAN to connect these two things, a LAN switch to connect these two. So as we talk about a switched LAN segment, I have LAN A here, which is a switched LAN, and I have LAN B here, which is a switched LAN. I connect them up using a switch. Now what happens in this case is that this will still get its complete 7 megabit per second traffic which it can use, and this will use a 6 megabit per second traffic, and both will be on two different collision domains. So the traffic over here will not affect the traffic over there, and the traffic here will not affect the traffic over here. So that is what we get, that is, you are able to extend and use the complete bandwidth effectively. So that is the advantage of using a switch. So the switch will only forward packets when necessary, and it will learn the network addresses of machines connected to each port. We just saw how this learning takes place. So if you look at switched LAN segments again, so they do not forward traffic between machines on same port, and it will provide packet buffering and retiming, and it will also reduce the collisions. Okay. So it also with respect to broadcast traffic, it does forward all broadcast traffic. With respect to multicast traffic, it may forward multicast traffic depending on the switch. So this is basically how the switched LAN segments will operate. So we will take a small break now and come back and continue on our understanding of extending LANs. Welcome back after the break. So we have been looking at how to extend LANs using bridges and switches. So I said one of the things that bridges and switches are used for is to basically extend the distance to which different LANs have been connected. So for instance, look at this picture here. I am talking about having two fast Ethernets, right. So this is, let us say, connected by means of a bridge, just a 300-meter segment that is used between these two, and I want to connect this to another LAN which is located, let us say, at about 40 kilometers from here. I could still use a wireless bridge to connect up these two. So this is also another possibility that we have with LANs, with these switches. Now with LAN extension, a switch can extend the length limit of network since it provides packet retiming and retransmission. A bridge could be used when you are using different media and protocols to extend the length limit. And switches are not subject to the repeater count limit on Ethernet. Remember that when we are using Ethernet and we use hubs or repeaters, we are limited in terms of the number of repeaters that you could use. But when you use switches, you are no longer limited by means of that repeater count which is normally there on the Ethernet. So you can see how bridges and switches can be used for LAN extension. Another thing we talked about is buffering. Okay, so in fact when we said that the buffering is something which allows you to do this extension. So how is it that the buffering is done? And why is it that the buffering is done? A bridge or switch may buffer frames because the output port may be busy, or on a token ring network, for instance, it must wait for a token. Suppose we are using an 802.5 network on one side, then which is a token ring network, you need to acquire a token before you can do the transmission. So in which case you will have to wait for the token before you can transmit. So until you receive the token, you will have to buffer the packets. Okay, so these are two instances, for instance, when buffering is required. So we will look at more instances now. So another thing why buffering would be required may be for doing speed matching, that is, input and output ports may not be of the same speed. I could have a 10 megabit per second input port and I could have a 100 megabit per second output port, in which case to do the speed matching you will have to do some buffering. Similarly, for doing protocol conversion, you need to buffer the frame, so that because you need to change the format. If I receive an 802.3 frame and I want to change it to an 802.5 frame, I need to anyway buffer it and then change the format. And frame buffering could also be done to eliminate fragments and error frames. So this is another reason why we would be doing some frame buffering. Now buffering can also help to reduce collisions. So let's look at how that happens. Now if I use a hub or a repeater will transmit all frames, right? We've just seen this immediately, even if it results in a collision. So if input occurs on two hub ports, the hub sends a collision presence signals on all ports. We have seen this. This is what happens in a hub. But the same thing if you have a repeater or a switch, you see that the bridge or a switch can buffer the packets to avoid collisions. Okay, so this is another interesting use of the, a more direct use of the buffering mechanism. So it obviously helps to reduce the collisions. So we just seen this. So an Ethernet bridge or switch uses the same CSMA CD algorithm as a host. So it buffers frames and retransmits the frame when the media is idle. So it kind of forwards the frames after doing the buffering. So as we saw on a token ring, it may buffer and wait for the token. So this is what we are seeing over here. Okay, when you have a switch or a bridge. Now when you are looking at different protocols, so as let's say I have an Ethernet protocol here and a token ring protocol here. So the bridge will now do protocol transformation, right? So it will change from an Ethernet frame will be converted to a token ring frame and it will be sent. This is what is done when you are bridging different protocols. So a bridge can convert frame formats. Of course, it requires compatible network addresses. For example, Ethernet and token ring are okay because both of them use 48-bit addresses. Both of them belong to the same family of 802 family of protocols, but not Ethernet and ATM because they are totally incompatible network addresses. So you cannot do the bridging at that level. What can also happen is the frame conversion may lose some information about the frame. This typically happens when you have data transfer between Ethernet and token ring. So token ring, for instance, has some additional fields like A, C bits and so on, which indicates whether the data has been copied or not, which is not there in an Ethernet frame. So when you are transmitting a token ring frame on an Ethernet, you may lose some information. So that is something you need to contend with. Another thing we said we use switches for is for speed matching. So this is an example of a switch where I have a 10 megabit per second Ethernet on one side. So I have a 10 megabit per second Ethernet hub to which this is connected, and then I may have a fast Ethernet hub which connects 100 megabit per second Ethernet, and then I also have a gigabit per Ethernet connecting a server and a fast Ethernet connecting another server. So you can see that this switch here will be matching speeds between 10 Mbps, 100 Mbps and gigabit Ethernet, right. So this is something which is possible with a switch. Okay. So a switch can connect segments operating at different speeds, and Ethernet switches can support 10 Mbps, 100 Mbps and gigabit switches. Now bridging Ethernet is simple because the packet formats are the same, so that makes it easier. Another use of bridges is for providing security. Okay, so let's look at what happens here. When I have a hub, again it's a shared media access, so everybody can listen to all the transmissions that are taking place. So a hub forwards all packets to all ports, so any host can listen to packets to or from another host using programs like TCP dump, etherwatch, snoop and so on. So these are different application software available which allow you to do eavesdropping and looking and find out all the data transmission that takes place in a network. But if I have a switch, on the other hand, the switch only forwards packets to ports containing the destination hosts. So other computers and other ports, they cannot eavesdrop. So it also provides a level of security. Now these are all the advantages of bridges and switches that we have looked at. Now let's look at some of the challenges that we have in bridges. Now one of the challenges that we have in bridges are loops. So loops in bridge networks, for instance, if you see this picture here, so I have different bridges which are connecting up different segments. So I could have a loop that is formed between these different switches that are used over here. So now why would I have a loop? Now it could either be accidental or it could be deliberate. Now what do I mean by saying it could be deliberate? It could be just provided for reliability. typically what happens is, let's say for instance I have different LANs which are connected up, I may just add another switch which in between just for providing reliability. Okay. For instance, if I have something like this, I have LAN 1 here, LAN 2 here, LAN 3 here and a LAN 4 here. I might already have a connection between LAN 1 and LAN 2 using bridge B1. I may add another bridge B2 here just to provide some kind of a reliability. That is, in case B1 fails, I may want to connect it up through B2. This is a possibility. Or it could be accidental. For instance, LAN 1 and LAN 2 may be connected up using a bridge 1. This may be extended to another LAN 3 by means of a bridge 4. This may be extended to LAN 3 by means of a bridge 5. And suddenly I may decide that I want to connect LAN 1 and LAN 3. So I put another bridge here which connects up these two. So the result is that you have loops that are there in the system. And these loops can create problems. Let us look at how a loop can create a problem. So let us say for instance, I have this LAN 1 and I have two bridges, right, B1 and B2, which is connecting up to LAN 2. So when LAN 1, let us say some node on LAN 1 transmits data, it will be received by B1, B1 will learn that it is coming from port 1 and transmit on to B2. Now the same packet will be received by B2, right, it will receive it on port 2 and transmit it again back onto port 1. So now what will happen is, there is a possibility that packets keep going round and round in loops between the two LANs. So this is a situation that we need to try to avoid, because the learning itself can keep on varying, because you will keep giving, now once B1 will get a packet from this side, next B1 will get the same packet from the other side. So B1 will really not be able to figure out which side that particular station really belongs to. It will keep changing the information that is there in its table. So we need to avoid this. How do we avoid this? The solution to bridge loops is basically by means of what's called as a spanning tree. So you need to build a spanning tree on the bridge, right, on this connection of bridges, such that you are able to find a path to go from one LAN to any other LAN without causing loops. Remember what we have in terms of a spanning tree. A spanning tree is basically a structure which will allow you to cover all the nodes that you have in a network, in a graph, without loops. So that is what is used in bridges also to avoid this loops. So let us briefly look at the spanning tree protocol. Now the spanning tree protocol is defined by the IEEE 802.1d standards, basically specifies an algorithm to be used to maintain a loop free spanning tree of links between bridges. Basically what I do is, see, let us say for instance I have different bridges over here, or the switches over here. Each switch is given some kind of an ID, and these switches exchange information between one another to find out which is the path that they should take in order to make sure that they are able to forward packets without getting into this loop problem. Okay. So the spanning tree algorithm finds a spanning tree that covers all the nodes starting from a root node. So you have something called a root node. They identify one of the nodes to be a root node and they construct a tree starting from that, a spanning tree starting from that root node. So the properties of the spanning tree would go like this. In a connected network, a loop free spanning tree always exists. So you should be able to find the spanning tree. The spanning tree algorithm will always stabilize on a loop free tree after at most number of nodes iterations. If there are 5 nodes, after 5 iterations it will definitely stabilize. The spanning tree of course may not be the most efficient path, but it helps to solve the problem of of loops that can exist when you have multiple bridges which are connected between the LANs. So in this example, for instance, you can see that once the spanning tree has been constructed, okay, you can see that if I want to forward from from this node to this node, I do not take this path. This path is dropped out of my graph because this does not come within this, it is not covered by the spanning tree. So instead I would go this way, I would go from 75, I would forward it to this bridge 40, from here I will go to bridge number 10, then to 80, and then it will reach this node. Okay, so which is why I said it may not be the most efficient path, but you will find a path where there are no loops. Okay, you can see that the light colored segment here indicates basically that this particular path is not being used for forwarding. So that is the way the spanning tree is used to solve the loop problem that we have in bridges and switches. Okay. Now coming to switching modes, when we talk of switches, there are different modes in which the switches can be used. One is called the cut through mode. In a cut through mode, we just forward packet as soon as possible, that is as soon as the destination address is known. The second is called a fragment free mode, where you buffer and check the packet header before forwarding. Now for Ethernet, you basically buffer and check the first 64 bytes so that you can avoid collisions. Remember that we need 64 bytes to detect the collision. So you buffer for 64 bytes and then you make sure that there is no collision, therefore you can forward the packets. Otherwise, you may also be forwarding packets which may result in a collision. So to avoid that, we make use of this particular mechanism. The third is a store and forward switching, where you receive the entire packet before you do the forwarding. Now these modes are used in both switches as well as routers. When we talk of switches, we talk of a layer 2 switch and a layer 3 switch. A layer 3 switch essentially does the job of a router. A layer 2 switch does the job of a bridge. So when you talk of a layer 2 switch and a layer 3 switch, both of them could use these three mechanisms, but here of course we are talking about layer 2 switches, so let us focus on that. So if you look at a simple say an 802.3 kind of a frame that is being sent, so a cut through switching will start as soon as the destination address is known, that is right at this point. Okay, we have destination address, source address, length, and then data followed by FCS. Now the fragment free switching will start at this point, that is after 64 bytes have been received, after it knows that collision has not taken place. Store and forward switching will start at this point, that is after the entire frame has been received. Okay. So to look at how this will appear, you can just look at this particular picture here. So this is our timeline. Sender is sending the packet to the switch. As soon as it gets the destination address, it will forward it to the receiver. This is what happens in cut through mode. In the fragment free mode, as soon as it has received 64 bytes of data, then it starts the transmission. You can see that there is a slight delay over here. Okay. In store and forward mode, after it receives the entire packet, then it does the transmission to the receiver, right. So it receives the entire packet and then it forwards it. So this avoids forwarding of damaged packets, and may also be needed if input and output port speeds are not the same. Okay. So this is something which is used for store and when store and forwarding mode of operation is used. Now if you want to do a quick comparison of the switching modes, for a 10 megabit per second link on an Intel 550T switch or router, so the delay through when you are using a cut through mode is about 0.03 milliseconds. Fragment free mode, it works out to 0.08 milliseconds, and store and forward for a 1 kilobyte packet will be definitely greater than 0.8 milliseconds. So store and forward delay of course depends on the packet size. So for fast Ethernet, the latency in cut through mode is 0.007 milliseconds. So you can see that cut through mode definitely gives you a faster mode of operation. Okay. Typical switch configurations would look like this. This is how a box would look like. It will have these different ports that are shown here, 8 to 24 ports for hosts, which can be 10 base T, 10/100 base TX and so on. And there will also be some uplink ports that we have for server or backbone, which can be connected to a fast Ethernet or a gigabit Ethernet. So typical switch configurations would look like this. You have an 8 to 24 10 base T ports, 8 to 24 10 or 100/auto sensing ports, then high speed link ports for connecting up servers and backbone connections. So this is how we basically connect up our different LANs using these switches. A quick summary on the different terms that are used over here. We use these terms: repeaters, hubs, bridges, switches, routers and gateways, right. So which device is in which layer? So this slide kind of summarizes that for you. Repeaters and hubs work at the physical layer, bridges and switches work at the data link layer, routers work at the network layer, gateways, transport gateways work at the transport layer, and application gateways work at the application layer. So all these are devices which are used for interconnecting different networks, but they operate at different layers. So this summary should give you, this slide should summarize whatever we have, what you need to know in terms of the different interconnecting devices. To summarize, what we have looked at is how the different LANs are connected together by means of repeaters, learning bridges and switches. So we also looked at the advantages of bridges and switches and how loops are avoided in bridging networks by means of a spanning tree, and we also looked at switching techniques. Coming to some questions that you can use to brush up the topic that we have learned today. Question number 1, at what layers do a repeater, hub, bridge and LAN switch operate? Question number 2, what is a learning bridge? Question number 3, does the bridge or switch buffer frames? Why or why not? Question number 4, can a bridge connect LANs of different protocols? Question number 5, why do loops occur in bridge networks? Question number 6, which algorithm is used to handle the looping problem in bridge networks? Question number 7, what is meant by cut through switching? Question number 8, you can just think about this, what is meant by a virtual LAN? Thank you.